Good afternoon and welcome to the Water Research Foundation webcast on decision-making framework for the prioritization of research into contaminants of emerging concern. My name is Michelle Suazo and I'm the communications coordinator and will be the moderator for today's webcast, stepping in for Julie Minton. I would like to run through a couple of housekeeping items before I hand it over to our presenters. Just quickly, just wanted to remind you, you are able to submit questions through the question box at any time. That question box is located on the left-hand side of your screen. We will hold all questions and we'll do a Q&A session near the end of the webcast today. Also wanted to say we do have a survey at the end of the webcast, so once we are done with our presentations and the Q&A, if you wouldn't mind just hanging tight and answering those survey questions once they appear on your screen. Also, the slides and the recording of the webcast will be available on the waterrf.org website within 24 hours of this broadcast. We do have two speakers today for today's webcast, and I wanted to introduce them. We have Stephanie Rink-Pfeiffer. She is the Managing Director with the Global Water Research Coalition, as well as we have Stuart Kahn, who is a professor in the School of Civil and Environmental Engineering at the University of New South Wales Water Research Centre in Australia. And with that, I'm going to turn it over to Stephanie.
Well, thank you very much, Michelle, for the introduction, and thank you to all of you for taking the time to tune in to this webcast. I will start by giving you a brief overview of the Global Water Research Coalition and how the project came about, and then I will pass over to Stuart Kahn, who will present the project objectives and outcomes. Now, the Global Water Research Coalition is a not-for-profit organisation, or coalition as it's called. It's got 12 members and 2 partners. The members being for the US, the Water Research Foundation, and as a partner, the US EPA. And then for Canada, we have the Canadian Water Network. And then moving on to the Europe, we have Acquia representing the UK, Veolia and Suez, the 2 French companies representing France. We have STOA representing the water basins for the Netherlands, and also KWR Water Cycle Research Centre for the Netherlands as well. The International Water Association is a partner. Then we have for Germany the Technologiezentrum Wasser representing research for Germany. Then moving on to South Africa, we have the Water Research Commission. Then we have in Singapore, we have PUB, the Singapore National Water Agency representing Singapore. And then for Australia, we have Water Research Australia and the Water Services Association of Australia. And we also have a new partner joining us from China, the Chinese Academy of Sciences, which are literally just signing up. So just to go through the vision and mission of the Global Water Research Coalition, really the vision is global cooperation for generation and exchange of water knowledge. And our main mission really is to maintain a strong partnership between the members and partners I've just listed, and it's really to generate and exchange and communicate our knowledge through research collaboration. And really the aim is to support safe and sustainable water supply and sanitation for the protection of public health and the aquatic environment, and we're really dealing with the entire water cycle. So how does it work? The Global Water Research Coalition, it's been operational since 2002. It's governed by an independent governing board of directors, and mainly most of the CEOs of each of the members that I've listed before and partners sit on the board, and the board meets twice a year. And it really is a network of those organisations that I've showed you that mainly coordinate research programs at national level. So you have seen there are no consultants or universities, they're mainly national bodies that have a research budget and also deal with the water cycle research on national but also international level. And how it works is that we have a research approach that is based on having a research agenda that is based on members' needs. So we set it together and we review it annually. And the projects are coordinated by the members. So, for example, this project that Stuart Khan is presenting today was led by Water Research Foundation, hence why the webcast is also organised by Water Research Foundation, and they were the lead agent for that project. And then the results are shared, and they're shared and transferred to the members and partners, and it's up to them then to share the results to their own stakeholders or subscribers themselves. And the benefits are really the leveraging of the expertise and resources, and also the prevention of duplication and replication of research. So the Prioritisation of Contaminants of Emerging Concern project that we're presenting to you today really came about via a GWRC workshop that we had in 2015 in Karlsruhe, where we looked at emerging issues and what research was of interest to the members and partners. And really what came about is everyone had the same questions on how do we prioritise contaminants. How do we know which ones are the most toxic, the hardest to treat, and the most unknown of those emerging contaminants? And it really came back to us saying, well, each organisation has a different framework and has a different answer to that and ranks them differently. So what we wanted to do is have a prioritisation framework, look at each of those organisations also from the membership and partnership that we had on how they did it, and then improve the decision making and come up with one common framework, and really also to lead to an informed policy making. So therefore, I will I'll pass over to Stuart, but also wanted to take the opportunity to thank all the partners to this project and also the PAC, which you can see listed here on those slides. And I also want to thank in particular Julie Minton from Water Research Foundation for coordinating this project on behalf of the GWRC. So with that, I'll pass over to Stuart Khan, who will go through the objectives and outcomes of the project.
Thank you, Stephanie. Yes, so it's been an interesting project to work on, and I'll talk you through what the intentions are and what we hope that the useful tool that we hope that we've produced at the end of it. So Stephanie just showed this slide, but I'll just mention again that it came from the workshop where a number of people were brought together to identify what are going to be the priority contaminants to invest research into. So the idea is that all organisations have a limited budget for research. If we had an infinite budget, we wouldn't need to do prioritisation. And I think at the start of that workshop, we were expected to more or less come up with a list. These are the priorities, and these are the things that we should be investing in. And we hit a roadblock fairly quickly in that people started to say, well, how do we even ask that question? How do we make that decision? What is the highest priority? Is it the most toxic chemical, or is it the hardest one to treat, or is it the one that we have the least information about? We don't know the toxicity. We don't know how well how to treat it. And then we realised quickly that there's no simple answer to those questions because it depends who's asking the question. It depends on the particular organisation, what they do, and it's also a very subjective question. It depends on the values in terms of how you would prioritise research needs. So ultimately, we went out to try and set up a framework to formalise these questions and to answer them in a systematic way as opposed to some kind of a gut feeling about where our priorities should be. So the first thing that we did was we organised a survey. The survey had two main objectives. One was to find out if there were any tools like this that were being used, if there were any decision-making frameworks for prioritisation, and to gather information about those tools and to learn from them to see whether we needed to come up with anything new or not. And if we did, what are some of the existing ideas and concepts that are working well and might be adopted? And then the second thing was to take a step further ahead in the process than that and think about the criteria. What are going to be the key criteria that we make these decisions on? And I'll come back to that point. So first of all, we had a large number of people, close to 50 organisations that completed the survey from various parts of the world, as you can see from the pie chart. The second pie chart, the one on the right, is more insightful. It tells us about what sorts of frameworks for decision making different organisations were using or were familiar with. As you can see, the big dark blue slice of the pie there says that the organisations were not using any sort of framework, formal or informal. The second biggest slice there, the green slice there, says that the organisation had some sort of an informal internal framework. It wasn't necessarily something that was written down that had specific steps, but they had some idea of how they make their decisions, how they come up with priorities. And smaller numbers then did actually have a formal internal framework, and much smaller, again, we're using some sort of an externally developed framework for decision making. So that's where we sat. There was no real consistency in the way that organisations were doing this. Some of them, many of them had some process, but many didn't. Others didn't have any process at all. In fact, the largest slice of the pie. One area of confusion, I think, when we started talking about prioritisation is, what do we mean by that? What are we trying to achieve? And a common suggestion that came back was to look at risk-based prioritisation. So, for example, we can look at what the European Water Framework Directive has done in terms of identifying a number of key trace contaminants that should be focused on for monitoring, and this is based on classic, well-established risk assessment methodology, where you might look at the exposure to a particular contaminant, you look at the toxicity of that particular contaminant, you pull those things together and you come up with some sort of a risk assessment, and from that identify priorities for monitoring, for control, etc. That's not the objective for this project. This project was all about asking what should be our priorities for further research. So it's a different question. We're thinking about where are the gaps in knowledge and where is the most value in filling those particular gaps. So we didn't take a risk-based prioritisation approach. Instead, the basic concept that was adopted was to use a multi-criteria decision analysis. So those familiar with the multi-criteria decision analysis will know the key steps as presented on this slide, where we would first of all start by identifying the decision problem. In our case, which chemicals should be most prioritised for further research. We would gather information and obtain the criteria. So in other words, back to some of the questions that we looked at the start, what is important to me if I want to undertake research on a particular contaminant? I'll be thinking about, is this something that might be present in the water that I produce? Is this something which it's known to be a highly toxic chemical? And various other criteria which we'll look at in more detail. Then we'll develop the alternatives, which in this case is the list of chemicals. If we can come up with some big universal list of chemicals that could be considered for prioritisation, and then evaluate each of those alternatives, each of those chemicals, against the criteria that we've identified. So this is one that's toxic, or this is not one that's toxic. We need to think about uncertainty, and sensitivity analysis is one way of dealing with uncertainty. We've implemented another way as well. In the tool that we've come up with, but we need to think about the uncertainty and the sensitivity of the way that we've scored the different criteria and the different alternatives, and from that information, somehow mathematically bring it all together with all of the different scores for different contaminants against the various criteria and come up with some overall prioritisation ranking. So we identified Bayesian networks as a useful tool just to bring that concept, just to do the maths, the underlying maths behind that multi-criteria decision analysis together. So the first tool, and the one I'll show you first, was developed using Netica, which is a Bayesian network software application produced by Norcis. It is possible to, you can obtain a freeware version of Netica that has sufficient capacity to be able to use the model that we've developed, but then I'll show you another way to access that model as well as we get closer to the end of this presentation. So a Bayesian network and the way that we've constructed it now, it can be used to prioritise by numerical rank order further research on the various trace contaminants that we identify. It incorporates standardised current methodology for multi-criteria decision analysis, and then the additional thing that we've added to that methodology, because it's essential in this particular application, is to incorporate uncertainty. We're making assessments, we're making judgments about particular chemicals and criteria with imperfect information. So there's always uncertainty, and we wanted to be able to capture that uncertainty in the process so that the final conclusions that we draw at the end properly reflect the uncertainty that went into the input data. So from that stakeholder survey, the 11 key criteria, and there are various requirements around the criteria in terms of them being sufficiently independent from each other. We identified 11 key criteria that may not be important to all organisations, but was important to a significant number, were important to a significant number of the organisations that responded to the survey. And you can look fairly clearly and quickly and get the idea of the sorts of things that we're talking about. So for some organisations, if they're thinking about will they prioritise a chemical highly for research, it might be all about, is this something that's regulated? Is this something our regulator requires us to keep an eye on, to understand, to manage? For others, it might be about the health risks. And so we ask the question, is it known or suspected to cause acute or chronic health risks? Is it toxic? A lack of information around the health risks might be a very good reason to prioritise a particular contaminant for research. Whether there's evidence for widespread or emerging public concern around that contaminant would be a driver for some organisations. I won't read through the rest of them, but you get the idea. There are a couple down there. There's one that talks specifically about, does this contaminant provide unique challenges to our organisation? Therefore, is it something that we should be specifically investing in research on? And other questions about, is it difficult to treat and to manage? One that's interesting, again, I've just about mentioned them all now, is the analytical techniques. So this is an interesting question because whether or not there are available analytical techniques, does that make you prioritise the chemical more highly or less highly? And that depends on who you are and what you do. If you're an organisation that develops analytical techniques, then that might be a reason to prioritise that contaminant more highly because there's some research for you to do there. However, if you're an organisation that would rely on the existence of a suitable analytical technique to characterise a treatment process, then that would make you prioritise that contaminant less highly. And so we deal with whether each of these criteria make the prioritisation higher or lower in any particular circumstance. So looking at the next slide starts to show us where we've built some of this information into the Bayesian network. So this is a screenshot from Netica, and we're going through looking at each of the different criteria questions. And so the first one is, has this contaminant been, or is it likely to be, regulated by a relevant regulatory agency to my organisation? We've tried to keep the questions as broad as possible. And then what would happen is that the decision makers, and the way that we picture this working in practice, most commonly and ideally, is you would have a group of people. So it might be a workshop scenario where various people from the organisation with various knowledge and experience in different parts of the organisation would come together and rate each contaminant against that particular criterion. So in this case, the options are that future regulations are unlikely. It's not something that's going to be regulated, or there may be regulations coming soon in the future, or regulations are currently in place. And so we've got these three different rating scores there. And then there's the question of confidence. How confident are we that we've selected the right answer there? Were people in the room in a workshop environment of mixed opinion regarding what the correct weighting would be, or is this something that we were very sure about? So in this example, the decision maker has selected that we have a medium confidence. So when you look at what that does to the result in the orange box there, it means that most of the probability density, if you like, is on future regulations are unlikely, because that's what we selected in the first box. But because that confidence is not high, it's only medium, some of that probability density has spilled over into there may be regulations in the future, reflecting that we're not absolutely certain of the score that we gave. And then the pink box there asks the question, is this a positive criteria? Is this something that would make us more likely to want to prioritise this contaminant, or is it negative, which would make us less likely to want to prioritise the contaminant, or is it neutral? Is it not something we even care about, that wouldn't influence our decision? That carries over then into the blue box, where we then identify for each of these criteria, each of the 11 criteria in the process, how important they are in a relative sense. So either if I'd selected this was a neutral criteria, that would automatically populate the not applicable box in the first blue box. Otherwise, we can select from it's relatively unimportant, it's moderately important, or it's very important. And again, this is associated with a level of confidence. So we would need to select that we have a high confidence, a medium confidence, or a low confidence. In this example, the user has selected a low confidence, which gives the result that you see in the green box, where whether the contaminant has been subjected to regulation or is likely to be subjected to regulation. Most of the population density there is in moderately important, because that was what was selected in the first blue box at the top. But because of the low level of confidence, it has spilt over into the adjacent two boxes. It could be very important, it could be relatively unimportant. And that degree of uncertainty carries through to the final result. The next two slides are not very interesting to look at, but they just show the way that Bayesian network is set up to deal with that uncertainty. So whether somebody selects a degree of confidence of high, medium, or low, defines how much of the probability density is spilt over into the adjacent categories. I could come back and look at that in more detail if people would like me to, but it's relatively straightforward. And the same for the next slide for the criteria scores. Whether or not we've selected a high, medium, or low level of confidence influences how much of the density of the decision is allocated to each of the three different scores of importance for a particular criterion. So for batch processing of the contaminants, if I just look at one individual contaminant and I come up with a priority score, it doesn't mean anything at all. It's completely meaningless on its own. It only starts to make sense when we've got a large number of contaminants that we're comparing with each other. It's all relative in this analysis. So we've set up a process whereby you can download an Excel spreadsheet, and you can enter that Excel spreadsheet with all of this information for a whole bunch of contaminants. Again, something that we would envisage would be done in a workshop type scenario, where we would identify for each of the different criterion what the score would be for that criterion, the associated level of confidence between high, medium, and low. Then the next slide looks complicated, but you get the idea, I think, that what it's doing is it's taking those 11 criteria and all of the scores and all of the weightings and all of the uncertainties for those 11 criteria and bringing them all together to come up with one single prioritization score at the end of that process for a particular contaminant. Again, that's a completely meaningless number, this 3.356. Plus or minus a standard deviation as shown. It means nothing in isolation. It only starts to have any value when we start comparing it to other ranked chemicals. So here's an illustrative example. We've got chemical A and chemical B. In this example, we've only looked at two criteria. All of the rest have been selected as not important. The two criteria, the first one is about whether or not there are regulations in place. The second one is about whether there are significant health risks anticipated. And you can see that for both of these chemicals, we've identified that there are regulations in place with a high degree of confidence. It sounds reasonable. You would know whether or not there are regulations in place usually, and from that is calculated through to give a mean and a standard deviation based on the 11 criteria, for which only 2 of them really contributed in this case. For chemical B, in this illustrative example, it indicates that future regulations are unlikely. We're not expecting that this chemical is going to be regulated, but only with a medium level of confidence. We can't know for sure, and therefore we end up with a different prioritization. We end up with a lower mean value for the prioritization for chemical B, because in this case we've said that we've selected that whether or not regulations are in place is an important criteria, and we'd be more likely to prioritize something for which regulations are in place. So you end up with a lower mean value. In this example, we can also look at the standard deviations, and we see that the standard deviations are in the opposite order, that chemical B has a higher standard deviation than chemical A, which means that there's a greater degree of uncertainty, which is a direct consequence of having selected medium confidence for criterion 1 for chemical B. In order to make the whole process more accessible and user-friendly, although it's a little bit more of a black box, you can't quite see what's going on as well if you use the web tool, but we have set up a web-based tool, and the URL for it is presented at the top of this slide, and it's available and active now. Don't do it while I'm talking, but as soon as I've finished you can have a look at it. And you can test out how this model works without having to download Netica or use any other type of software at all. It's based on some Excel spreadsheets which can be downloaded from the website. So there are 2 models that are available on that website. The first of them is just for looking at one chemical, which is useful for just getting an understanding of the sensitivity, how the process works. But probably the more useful model is the second one, which is for multiple chemicals, where you would download a spreadsheet, work through a workshop where an organisation would come up with their ratings for the different criteria, contaminants and levels of uncertainty, and then upload that particular workshop and come up with some conclusions. So this is what you would see on the screen for if you use the one chemical at a time model. It merely goes through and asks all of those same questions that I just showed you in the Netica format, the weightings and means for the particular criterion, the uncertainties in terms of confidence in what's selected, whether it's a positive, negative or neutral type of influence, and then looking at how each particular contaminant ranks against each of the different criteria, again associated with a particular level of confidence. And at the end of that process, it spits out some summary statistics, most usefully I think being the mean value, in this case 1.40, and the standard deviation that we looked at previously, 0.77. There's a couple of other statistical values produced as well. More usefully, I think, is using the model for multiple chemicals. In this case, when we look at the criteria, all the criteria are constant. They relate to all of the chemicals, so we don't need to reset those criteria or reassess those criteria for each individual chemical. We need to think as an organisation how important each of those criteria are to us in terms of wanting to prioritise contaminants. So we go through the criteria, number 1 to 11, as we've seen before. We identify a type of influence, positive, more likely to want to prioritise, negative is less likely to want to prioritise, neutral means it's not important to us, it's not something that we would consider. The weighting for each of those criteria, some of these are relatively unimportant, some of them are very important, and anything that we said was neutral will come across as not applicable. Is also moderately important. And then the level of confidence in that weighting. This is something that we all agreed on, would be a high level of confidence. There was a bit of variability in people's opinions, which might have led us to a medium level of confidence, or really there was quite a lot of uncertainty around the way that we selected the importance of a particular criterion, which would be a low level of confidence. And then we would go through a second spreadsheet where we would have our list of chemical contaminants. So in this case, it's just showing 3 examples. And for each of those contaminants, we would rank them against each of the 11 criteria. So this is just the first criteria showing here, and 3 different options: that future regulations are unlikely, there are regulations in place or under development, and there may be regulations in the future, and a level of confidence associated with each one of those. Then you can upload those spreadsheets, so they're both available on the website to download, but then you re-upload them by this format that I'm sure you're all familiar with. You press the browse button, you find it on your hard drive, and upload a CSV file, and that CSV file will then process, and so there'll be a processing bar at the bottom right of the screen showing here that we're up to case number 10, chemical number 10 out of a large list of chemicals that it's processing and developing the score. Then at the end of that process, we would end up with these summary results, which would rank the chemicals in order of their mean chemical combined, CPI in this case stands for combined prioritization indicator. So they would be ranked in terms of their combined prioritization indicator. It also shows the standard deviation, so we get a sense of the level of certainty and whether or not adjacent chemicals really overlap with each other based on the implied uncertainty. And it also shows us in the last 2 columns which were the criteria that really drove that conclusion, which were the criteria that contributed most to bringing this particular chemical up to the top. So this example that I'm showing you here is just made up results, but I'll show you a case study in a moment. In fact, here's the case study. So we went through a process with a small water utility in Australia with a research manager who, under direct discussion, we sat down and we talked about which are the various criteria that would be important to that particular organisation. So they were all ranked positive, negative or neutral, and then a weighting in terms of how positive, negative or neutral, how important, very important, moderately important, or relatively unimportant was applied to each of the different 11 criteria, and then the level of confidence associated with that particular ranking. So this particular case study reflects that one organisation's values and research needs, I suppose. Then we came up with a list of candidate chemical contaminants. In this case, we didn't have one handy, so we simply downloaded the US EPA candidate contaminant list, the number 4 candidate contaminant list that came out at the end of 2016. And use that particular list as a representative list of chemical contaminants that this organisation might prioritise research for. But of course, any list of chemicals can be used in this process. And we went through the process then and scored each of the contaminants against the criteria and came up with this real prioritisation ranking for that particular organisation. And for that particular organisation, it says, well, the chemical that it's pointing to for us that we should be investing in research for is PFOA. It's probably a fairly realistic outcome for many water utilities at the moment. With a combined prioritization indicator, in this case of 1.88, also presents the standard deviation as we've discussed, and it shows us the most important criteria that really drove that conclusion. And the most significant criteria that drove it in this conclusion was that the criteria around whether or not this chemical is particularly difficult to manage by our conventional treatment processes, by the treatment processes that we currently have. And that's because this organisation had found that this chemical does turn up in the final treated water, so it's not being effectively treated by the treatment processes in place. And the second most important criteria was whether or not the chemical is or is likely to be regulated in the future. And everybody knows that this is a chemical that's very much on the radar of regulatory organisations. So again, that made a lot of sense to see that come up in this conclusion. Then you see there are a bunch of chemicals that came up prioritised very closely to each other with a standard deviation that shows significant overlap between those other scores. So this is just one example how one organisation ranked these chemical contaminants, but it does show that the next big box, the next big group of chemicals, there really isn't a lot distinguishing them in terms of their importance for further research, even though there are different things that are driving those conclusions. So the first box have issues related to health risks associated with them that rank them highly, and then from the fifth chemical down on that list, then the key issues became the possibility or actuality of regulations and the availability of analytical techniques to be able to measure these contaminants. So through this process, we've identified a tool for research prioritisation. A key thing to understand is it doesn't provide the answer. I don't think there will ever be the answer, because the answer is very much organisation specific. It depends on what your responsibilities are, what types of water that you deal with. It depends on your local regulatory environment, and it very much depends on the values of the organisation. Does this organisation see them somebody that's pushing the envelope on new research into unknown contaminants, or is it an organisation that's merely trying to do its job and comply with existing requirements? We've identified some broadly applicable criteria, the 11 criteria that we've talked about, identified that a multi-criteria decision analysis suits the task. That's ultimately the question that we're trying to answer here, is how do we select a conclusion based on multiple criteria, each of different importance or significance. And we found that a Bayesian network is convenient in terms of doing the maths in a way that helps us particularly to capture the uncertainty around the various criteria and the various scores for different chemicals and carry that through to a final conclusion. And that online tool, as I mentioned, is available at the URL I showed you. It also has I think it has my email address on it, but it also has a discussion board there, and it would be great to get any feedback or any questions on that discussion board of organisations that are trying to use it. And I'm sure it's something that can probably evolve over time as good ideas come through or people struggle with particular aspects of it. Okay, I think that brings me to the end, and very happy to take any questions that people may have. Thank you.
Thank you very much, Stuart, for an excellent talk. And we have time for questions. And if you still want to ask a question, you can write them. You'll see that on your screen, questions and answer. So we've received a few questions already. So I'll start with the first one, actually, Stuart, for you. There's one here, I'm sure you can see it, where the 11 criteria given different relative weightages.
Yes, so that Rai might have asked that question before I got to that point, but yeah, that's a key part of the process, is to identify how important each of those 11 criteria are. Yep.
And then you said also some criteria seem more important than others.
Indeed. So I suspect Ryan made that comment before I explained it, where absolutely some criteria be more important than others. Some are not important to particular organisations at all, and some of them will be very important, some of them will be moderately important, and some of them will be relatively unimportant, and we rank them accordingly.
Right, yep. Okay, all good. Then there's another question here. Utilities are already aware that contaminants that have been regulated are a higher priority than those that may or may not be regulated. We are more concerned with how to prioritise information gathering on contaminants for which impacts are poorly understood or which are difficult to measure. The questions explored here presume those answers are already present, unfortunately, but could you imagine a way to offer guidance earlier in the process?
I partially agree with that interpretation, but not entirely. So we've got 11 criteria. For some people, whether or not it's regulated or not will be important, and for other organisations it may not be so important, as pointed out in the question. So you can cancel out that criteria by selecting that this is a neutral criteria, so it doesn't get calculated then, it doesn't get used then in the overall calculation. And there are indeed other criteria further down the list which are specifically about whether or not a contaminant is difficult to measure or difficult to manage in a particular water treatment process. So I think this tool does exactly what this question is suggesting that it should do, in that it should be able to select the right criteria for the right organisation. That's part of what it does. So can you imagine a way to offer guidance earlier in the process? Indeed, I think you could be thinking we need to be thinking about what the criteria are and whether or not the right criteria have been selected for this particular application. It is possible to completely rewrite the criteria if organisations decide that this list of 11 are not the right criteria, are not hitting the mark for their particular organisation. They can be replaced with any other criteria, as long as we're careful about making sure that they're independent of each other.
Mm-hmm. Okay, I'll continue through it. Some more questions coming in, and one's probably more on the case study that you presented, asking, was only PFOA assessed amongst the myriad PFAS chemicals?
In this case, I think it was, but that's because only PFOA was on the list that we happened to use. I mentioned that we used the US EPA candidate contaminant list, number 4. So whichever chemicals were on that particular list were the ones that were assessed. But again, it's not about the particular outcome for that. In this case, it's about each individual organisation thinking about, well, what might be an appropriate list of candidate contaminants in their case, and how would they rank and score each of those candidate contaminants. So the process itself is just as useful and just as applicable, first of all, to any other PFAS chemical that you might want to look at, but it's also entirely possible to answer most of these criteria in more general terms too. So you could talk about perfluorinated chemicals in general without having to identify any specific chemical contaminant.
Yep, okay. Then we have one here on how would this process be modified to also include microbial contaminants?
That's a good question, and it would be. I think the multi-criteria decision analysis concept makes sense because all those decisions are based on multi-criteria. But then we would need to think about whether the 11 criteria that we've identified effectively apply to microbial contaminants. In some cases, they may not apply quite as well. But I think the maths, the framework that we've used using a Bayesian network could be easily adapted. It's just a matter of thinking about the criteria and how we would score the different microbial contaminants against whichever criteria was settled upon.
Mm-hmm. Okay. There's one here, it's more a comment or suggestion, just saying the Australian Department of Environment has their own tool to prioritise chemicals of emerging concern. It'd be good to compare the results from this project with their assessments on many chemicals. That's just mainly a comment.
So that's true, but
yeah.
I would only make the point that that's true, but it would need to be the Australian Department of Environment that used the tool to do that, because you'd be comparing the priorities of that particular organisation against their priorities as they've expressed previously.
And then we have here, and I think it goes back to one of the answers you gave, does your web-based tool allow you to add additional criteria?
So additional, anything's possible. It's just a Bayesian network. It's possible to modify it. Additional criteria is a little bit more difficult to add. It's something that I could add if people wanted that in there. But it certainly allows you to replace criteria. So currently it's set up for 11 criteria. If some of those 11 are not right, they can be replaced. But it's a little bit more work, not impossible, to add more than 11 criteria.
Right. Then we have here one on, does the criteria consider state of of what other organisations are doing to avoid going it alone on research?
Not explicitly. It perhaps should. I think that there is a question in there about whether there's a lack of knowledge, whether there are current couple of criteria that specifically refer to a lack of knowledge, so whether or not it's something that we don't think that information is out there. But that's a good point, that they, especially if you think about something like PFAS, for which everybody's diving in at the same time. There's lots of work going along in parallel, most certainly, and that's something that should be taken into account. So the answer is probably no on that one at this point, but it's a further consideration that should be taken into account.
And there's one here on standard deviation. If the standard deviation is pretty wide on the mean results, how to interpret different priority scores?
So again, the thing is to remember that there's no rocket science going on here. We're taking an organisation's opinions, an organisation's beliefs and knowledge, and just bringing it all together and reinterpreting it in a formalised structure. So if we find that we have standard deviations or conclusions that overlap with each other, what that's telling us is that there isn't a big gap that should lead to why we would prioritise a particular pesticide so much more highly than another pesticide or other contaminant. So I think in that circumstance, you could either take that as a conclusion that all of these things are pretty equal priority, or you could play around with the sensitivity analysis, and you could think you could collect more information. There are ways to narrow the standard deviation, and narrowing the standard deviation comes from reducing the uncertainty. So if the question's asking things about whether or not this is likely to be regulated in the future, or whether or not this chemical is toxic, then it's possible that if you've answered that we'll have a very low level of confidence in the answer that I've given, then that tells you, well, if we go out and we do some research and we find out, the regulation really is on the way, or there is known toxicity for this chemical contaminant, and we can start to reduce our uncertainty levels or increase our confidence levels, then that will reduce the standard deviation. So that's one way of dealing with that scenario. Okay.
We've got 7 more questions, Stuart. I know you might want to have a glass of water in between.
All right.
Next one is on from Australia, from WASA. Is the environmental impact acute and chronic captured and incorporated in prioritisation?
I think the answer was yes. Let me pull up my own copy of the slides and just look 15. Back at the criteria. So no, in the 11 criteria that we have, they don't specifically refer to environmental impact. They refer only to chronic or acute health risks. That was absolutely one of the questions that was in the original stakeholder survey that went out. It was a much longer list of potential priorities and criteria, and it just happened to be one that was ranked more lowly by the various organisations that responded to that survey. So it didn't make it into the top 11 criteria from the survey. Potential environmental impacts. But again, there's no reason why any particular organisation can't replace one of those 11 criteria with something that is a more significant component of their overall decision making.
Right, okay. Next question is more on prioritising pharmaceuticals. So it says local prescription rate data can be useful in helping to prioritise pharmaceuticals. Is there a way to capture this information in your existing tool?
Again, if there are questions around whether or not it's something that's likely to be present in the water that we produce, etc. So one would think that there's some relationship between levels of use of particular contaminants and the likelihood of presence. So in a sense that is captured, but again, I think the answer is that if a particular organisation feels the rates of use or rates of prescription of pharmaceuticals is something that to them makes them want to prioritise a contaminant more highly, any criteria can be written into the criteria list. So you could specifically identify that as a criteria, that this is something for which certain number of or certain mass of prescription is known to occur in a particular area per year or something. But so the answer is yes, it's not there explicitly at the moment, but the tool is flexible enough to be able to incorporate that.
Okay, very good. Next one talks about the list. So here it says the tool looks useful when you have a list of CECs, but it still needs input from such a wide variety of knowledge sources to form the original list of CECs, which is really the real question. How do you create that CEC list? Yeah,
so I agree. That's it's not a tool that takes away the time requirements to be able to do the prioritisation. It's data heavy, or at least opinion heavy, and you need a process to be able to go through and collect that data, and that's the biggest hurdles, the biggest obstacle to being able to do the prioritisation. As I mentioned, in this case, we borrowed somebody else's list. We borrowed a US EPA list. But if there's a different list, an organisation could think of many ways to come up with a candidate list, and one of them might be by doing a survey within the organisation, or a survey of other stakeholders. What is it that people can recommend that might be considered for prioritisation?
Mm-hmm. Okay. Next one is on analytical measurement here. For items like the analytical measurement sensitivity, where the ability of measurement is the same industry-wide, could an industry standard response be developed for the majority of chemicals?
That's a good point. In fact, even going beyond that suggestion of just analytical measurement sensitivity, we could think about toxicity, etc. I think it would be very useful to have some sort of a database that people could refer to when answering the questions about what is known and what is unknown for a chemical contaminant. So the answer is yes, we don't have that at the moment, but I clearly get the usefulness of that suggestion.
Mm-hmm. And we have one here from the University of Washington about the strategy for dealing with the overlap of the rankings, whether you ended up with broad groupings, maybe ranked high, medium, and low. Interested in hearing about the approach you used.
Yeah, I mean, there are lots of ways that we could provide this ranking. We thought about even using a slider bar, which would give you a lot more flexibility between high, medium, and low. But ultimately, when it came down to it, we thought about whether, are you aware of regulation? Are you aware of the toxicology around this particular contaminant? There probably isn't going to be a lot more sensitivity in people's knowledge than simply high, medium, low levels of confidence. Either you are or you aren't. Again, the spreadsheet can be changed, the tool can be changed to incorporate more sensitivity, more nuance within those rankings, but we thought that the very broad categories were probably most realistic in terms of what sorts of knowledge and levels of certainty would be available.
Okay. We've got 5 more questions, Stuart, and then we'll have to stop there. Next question is, how do you deal with the unknown chemicals?
Yeah, good question. In this tool, I guess that isn't what we set out to do. The task was to think about the chemicals that are known and how would we prioritise those. It may be possible to think about coming up with a category of unknown contaminants as a pseudo-chemical contaminant, and think about how you would respond to each of these criteria for a hypothetical unknown chemical. I think it would be fairly difficult though, because you'd have a very high level of uncertainty on practically every criteria. So it's probably not the right tool for asking the question about unknown chemicals.
Next phase, I guess. Next question, what kind of separation between ranking values would be considered significant? How does the standard deviation come into play?
So similar to a question that we had previously.
Yeah, exactly.
I spoke about some suggestions on the ways that people can deal with that. Another answer, I guess, is the way the distributions, the normal shaped distributions that are implied in those rankings for uncertainty, which lead to the standard deviations. They're flexible as well. So if through experience, and to me it's only through experience that you could draw this conclusion, but if through experience you find that the model is not producing, is not passing the laugh test, that there should be more or there should be less uncertainty associated with some of the conclusions that are drawn. That's a very easy thing to change. I sort of glossed over 2 slides in the presentation that talked about those criteria weightings, and they're just numbers that are plugged in to describe the shapes of the distributions around the uncertainty. So they can be tightened up and they can be broadened if we find that that's an appropriate thing to do.
Okay. 3 more questions, Stuart. That one I'm not really clear whether it's about the ranking, but what about the terrestrial environment impacts from land application of effluent or recycled water?
Yeah, so this tool is only going to be effective if we're asking questions about specific chemical contaminants and where should we be investing on research for those chemical contaminants. I think that leads into the question that's asked about the overall environmental impacts of using water that contains lots of chemical contaminants, but the tool won't answer that question directly.
Okay. Are the presence of microplastics possible to prioritise?
Yes, they are. It's possible to go through the same process. You might ask yourself whether or not those 11 criteria are spot on for microplastics or not. But again, as I mentioned, that we could use broad categories like PFAS, and you could use a broad category like microplastics to assess whether or not these are things that have criteria associated with them that are going to lead to a high ranking for prioritisation. So yes, the concept applies, might require a little bit of tweaking in terms of the criteria.
Great. Okay. Last question for the webcast, and I quite like this one actually. With the WHO One Health focus, should the criteria be changed to include human health, environmental and animal health inputs, particularly in an antimicrobial resistance world?
The answer is quite possibly yes, and particularly if that's the values or the opinions of the organisation that is making the decision. The criteria should be changed to reflect whatever are the key criteria from the particular decision maker's point of view. So yes, that's the way it should be managed, and it's entirely possible to do.
Yeah. Okay, great. Well, thank you so much, Stuart. There's been a lot of questions to go through. Thank you for an excellent talk as well. I'll pass over to Michelle just to close the webcast.
Very good. Thank you very much, Stuart and Stephanie, for a great webcast today. Just wanted to remind everyone that the recording of this webcast will be available on the website, as well as the presentation slides. And if you wouldn't mind, once we finish here, if you would just hang tight and answer. We have 3 survey questions at the end here that we would love to get your feedback on for future webcast. And with that, have a great evening and a great day in Australia, and thank you very much.
Thank you all.
Thanks,
Thank you. Bye.